Hello, my name is Nem, and welcome to my Lab 5 for Physics 2 on magnetic bracking with Faraday's Law. So the purpose of this experiment is to observe the time-varying magnetic field in relation to a Curly magnetic field using Faraday's Law, and to predict, collect, and computationally represent this data of a magnet falling through a conductive tube of aluminum foil. And some brief overview of the results is that the experimental time for the magnet falling from the aluminum foil tube top is 2 seconds, and the computational time is about 1.9. So the physics principles and science background of this experiment are the Biot-Savart law, which will help us calculate the magnetic field. Also Faraday's law, which relates voltage with the number of spins in a ring, the time, and the magnetic flux, and also calculating the magnetic flux calculation, which is the integral of the magnetic field per area. We'll also discuss Ohm's law, which relates voltage to current and resistance, Newton's second and third law, which means that force is a change in momentum over time, and that every force has an equal and opposite force. And some other important information is that the system is the magnet and the aluminum foil tube. The surroundings are any other outside forces, and the assumptions are that non-neutral forces do not affect the system, and only gravity is accounted for extra forces, and drag is also negligible. So the details which I've kind of discussed is that I have a magnet with the north side facing towards positive Z, and I'm dropping the magnet 6 times through like an aluminum foil tube, and I also used an iPhone in slow motion video to record how long the fall was, so that way the human error on that was minimized, and I averaged the time for the magnet to fall to be about 2 seconds, and then below you can see some dimensions of the tube, and the radius, and the mass, and mu, which I calculated in Lab 3. And here I'm just showing a little free body diagram and representation of what the experiment looked like. As you can see, the magnet's at the top and it's going to fall, and F magnetic will be pointing towards positive y, while gravitational force Fg will be pointing towards negative y, and then that's the phone that was set up to record it. And then I'll just gloss over this, but this was the mu calculations that I used from Lab 3, and if you want to see that, you can look at it in my YouTube channel. Alrighty, so let's jump into the code. First we have the physical constants, which I mentioned earlier, just with the dimensions of the aluminum foil tube. And then next I use the Biot-Savart law to calculate mu, and also to just generally calculate the magnetic field. And then I calculate the magnetic flux, which is again the integral of the magnetic field times the change in area. Alrighty, and then the last thing that I had to do was just put everything together, like the free body diagram, where I accounted for the gravitational force pointing downwards, then the magnetic flux for every single ring in the tube, just making sure that the magnetic field was calculated per the change in area, and then calculating the magnetic force, the net force of the gravitational and magnetic force added together, and then because this is a loop function, I had to do a position and velocity update for every single ring as it was falling down. Alrighty, and then here's the results. So the experimental time was 2.05 seconds, while the computational time was 1.946 seconds. The image you see in the top left is the blue is the north end of the magnet and the red is the south, and it's just showing it falling slowly. And then we also have a graph of velocity versus time. And then as you can see, the experimental and computational do not match, so the error is a little higher than 5%. And some of the errors that I included on this were not accounting for the drag force as the magnet fell, other non-neutral magnetic field forces in the surroundings, also neutral magnetic forces such as my hand, which was on the tube, and also on the magnet when it started. And then just my own error when measuring the dimensions of the tube, the length, the radius, the width. And then also just stating that while my phone was the most accurate way to measure time, it can never be perfect. And lastly, movement of the foil pole that could have happened with contact with the magnet, my hand, maybe some wind in the room. Alrighty, so then for the what ifs, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So because resistivity and currents are inversely proportional in Ohm's laws, if the resistivity is decreased then the current is increased, so the time that it takes the magnet to fall through the aluminum foil tube would increase. And then what if there were holes or slots that were cut into the rings of the tube? How would this affect the ring currents in your model? So because the current would be decreased, the magnetic field as a whole would be weaker, so the time that it would take the magnet to fall through the aluminum foil tube would decrease since there's nothing that is holding it to go up. in that force. And thank you for watching.